All right, guys, so this is the second video to section 12.2. So if you haven't watched the first video, make sure you watch that first because this will make absolutely no sense if you haven't watched that. All right, so we are to example 5, okay? And it says here, a quality control inspector checks for defective parts. The table shows the results of the inspector's work. So here's our table, and this table makes our life a whole lot easier, okay? So there's two parts to this question. One, we want to find the probability that a defective part passes. Okay, so probability that a defective part passes. Okay, and part 2 is the probability that a non-defective part, so the probability that a non-defective fails. All right, so we can get all this information here. Okay, the first thing I want to do is I want to look at just the defective parts. Okay, if 3 defective parts pass and 36 fails, that means they tested a total of 39 defective parts. Okay, and then if I look here at the non-defective parts, if 450 of them pass and 11 of them fail, that would mean they tested a total of 461 defective parts. Okay, so when I say what's the probability that a defective part passes, I'm only looking at this table. I don't care about the non-defective parts. That has nothing to do with whether or not a defective part passes. Okay, so out of a total of 39 defective parts, 3 pass. So the probability that a defective part passes is simply 3 out of 39, which reduces to 1 out of 13. Okay, so it's the same thing on part 2. I want you to figure out what's the probability that a non-defective part fails, and once again, we're only going to look at this non-defective column because that's all that matters. So go ahead and do 2 on your own, and then we'll go over it. All right, so when we talk about non-defective part fails, we have a total of 461 parts that were tested, and of those, 11 failed. So 11 over 461, which doesn't reduce, that would be our probability. All right, let's look at number 6, A and B, and then we'll be done. Okay, these are a little more difficult where we're going to have to use our formulas. All right, so it says at a coffee shop, 80% of customers order coffee. Okay, only 15% order coffee and a bagel. What is the probability that a customer who orders coffee also orders a bagel? All right, so we're interested in 2 things. We're going to let the probability of A be the probability that they order coffee. Okay, and then the other thing we're worried about, do they order a bagel? So the probability of B, we're going to let that be the probability that they order a bagel. All right, so what it's asking, what is the probability that a customer who orders coffee also orders a bagel? Okay, so that would be the probability of they order a bagel given that they ordered coffee. Probability that bagel, given that, ordered coffee. Okay, and this is what we're trying to find. Okay, this is our magic thing. Okay, because we're trying to find this, guys, that should tell us that this is a dependent event. We're only worried about whether they ordered coffee or not when we're getting a bagel. So we would use probability of A and B equals probability of A times the probability of B given. Okay. All right. So we need the probability of A and B. That would be the probability that they ordered a coffee and a bagel. All right, so let's look back at what we highlighted up here. So at a coffee shop, 80% of the customers order coffee. So the probability they order coffee, 0.8. 15% of the customers order coffee and a bagel. So the probability of A and B is 0.15. Okay, we don't know the probability that they ordered a bagel given that they ordered a coffee. Okay, that's what we're trying to find out. So I'm going to use this formula right here. So the probability of A and B equals the probability of A times the probability of B given A. Okay, well the probability of A and B, guys, is right here. It's 0.15. So 0.15 equals the probability of A is 0.8 times the probability of B given A, okay, which we don't know. Okay, so to get probability of B given A on its own, all we're going to do is divide by 0.8, divide by 0.8. Now 0.15 over 0.18 is 0.1875. That's going to equal, those go away, the probability of B given A, which is exactly what we want. If we wanted to write that as a fraction, 0.1875 is 3 over 16. So either one of these would be okay. All right, I know this might be a little difficult, but I want you to go ahead and try to do this example here. Use the one we just did. It's pretty much the same exact way. And go through and do this one on your own. Then we'll go over it. All right, so this example says, at a school, 60% of students buy a school lunch. So I'm going to let my probability of A be the probability that they buy a lunch, which 60% is just 0.6. Okay? Only 10% of students buy lunch and dessert. Okay, well, I already have a probability of lunch. So I'm going to let my probability of B be the probability that they buy dessert. Okay, and therefore, the probability of A and B, okay, 10% of students buy lunch and dessert, so that would be 0.1. What I want to find is what is the probability of the student who buys lunch also buys dessert, okay? So what is the probability that they buy dessert given that they buy lunch, okay? We don't care about all the others. Okay, so we could also write that a probability of B given A. Okay, so we're going to want to use our dependent event formula, which is right here. The probability of A and B equals the probability of A times the probability of B given A. Well, the probability of A and B is 0.1. The probability of A is 0.6. So 0.1 equals 0.6 times the probability of B given A. Divide by 0.6 on both sides. I get 1/6 equals probability of B given A, or about 0.167. So, in other words, 1 out of 6 students who buy a lunch also buys a dessert.